Hello, chemistry students. So today we are looking at an introduction to heat. We've seen a little bit about heat already, all right? But I want to go into a very specific equation today that we need to master. So I highly recommend pause this video. I would have out a calculator. You can get away without a periodic table, but have a calculator, have a notebook ready, and just put the phone away. You'll be good to go. You're gonna be using the calculator the whole time anyway. All right, so we have already seen exothermic and endothermic reactions. Right, exothermic, they are hotter than their surroundings. They give off the heat. Right, we've talked about heat rolling downhill, so it's going to move away from the hot source towards the surroundings, the cold source. And an endothermic reaction, it actually gets cooler than the surroundings, and the heat goes into the system. All right, so we've seen that. We've seen delta H. If delta H is positive, it's endothermic. If delta H is negative, it's exothermic. Delta H being the enthalpy change. And we said enthalpy, it's a fancy way for saying heat, right? They mean the same thing. So we've talked about heat, but now we're going to look at a special equation to solve for the amount of heat. But before we do that, we're going to talk about the kinetic molecular theory. All right, so the kinetic molecular theory, it's the theory that all matter is made up of particles, atoms and molecules, and we abide by that, we're fine with that, moving constantly in random directions. All right, so everything's made up of atoms, and we could have atoms or molecules, but they're moving randomly. And they all have all of those particles, all of those atoms, and all of those molecules, they have kinetic energy. All right, kinetic energy, it's a topic in physics. The formula, which you do not need to know, kinetic energy equals 1/2 mass times velocity squared. Now, when particles collide, kinetic energy is transferred. So here we have our first example. This is a gas. The particles of gas, they are randomly bouncing around inside the container. All right, now the reason we have the bowling ball hitting the pins, right, when they collide with each other, they just bounce off. They don't break though. Right? Think about when you go bowling. The pins never break, they just kind of bounce around. So the kinetic molecular theory, it helps us understand all of the states of matter. All right. So we have our gases, they're spread out. Our liquids are close together. Our solids are very close to each other, tight, compact. We know that a solid has a definite volume and a definite shape. All right. And that's from its structure. We know that the liquid has a definite volume because the particles are very close to each other, but since they can slide past each other, the liquid has an indefinite shape, right? It takes the shape of the container it's in, and the gas, because they're so spread out, the gas has both an indefinite volume and an indefinite shape. And actually, I saw a very funny picture earlier this week. It was the social distancing of molecules, and the gas was the only appropriate one, right? So you got to be, more than 6 feet away, these gas particles in that joke. All right, so kinetic energy is the energy that objects possess due to their motion. All right, so 1/2 mass times velocity squared. So if someone's really big and they're running really fast, they have a lot of kinetic energy. All right, whereas a small person, maybe moving not that fast, doesn't have a lot of kinetic energy. So it all has to do with how big you are and how fast you're moving. All right. So now, what does kinetic energy have to do with us? Well, thermal energy, right? So temperature and heat. Temperature is related to the average kinetic energy of the particles in a substance. So when we talk about the temperature of something, we're really talking about its kinetic energy. To go even further, we're really talking about the speed of the molecules. So here we have a guy who's using iron, and he's making a horseshoe, and we can see it's glowing red, it's in the fire. That means that those solid particles, they're vibrating very quickly. All right, they're in motion, and their motion has to do with their temperature, and that horseshoe, it is red hot. You would not want to touch it. Now, when it cools off, here we have our homeboy over here using it. It is cooled off. We can see what the molecules of the atoms look like. They are vibrating significantly slower. All right, so it is cool to the touch. And now he can throw it. Now he can play his horseshoes outside. He's having a great time. All right. So really, when we talk about kinetic energy or thermal energy, all of this stuff, all of that energy, it's really just another way of saying the temperature. And we know if something's hot versus if something's cold. All right. So temperature is a measure of kinetic energy. All right. And again, the way a thermometer works, right? The surroundings of the thermometer come into thermal equilibrium. That's why, when a parent of yours has to take your temperature when you think you're sick, it has to take like a minute or so, right? You have to put it in your mouth and you have to wait a minute because it has to reach that thermal equilibrium. The substance inside the thermometer or the digital ones, it'll react, right? And it's looking at how many collisions are happening. So it's measuring the thermal energy. It's measuring the kinetic energy. We read that just as a temperature though, right? 98.6 degrees Fahrenheit, 200 degrees Celsius. We use the Kelvin scale, all fine, right? For us, we're only going to use Celsius and Kelvin. We're not going to use Fahrenheit, sorry. All right, so now heating solids. All right, in a solid, the particles, they are arranged in kind of like a fixed pattern, and they are vibrating, right? So when you have a solid just sitting there on your desk, the particles are in motion. It's not a fast motion, but they are able to vibrate back and forth. All right, now when you heat a solid, they're not able to really expand all that much, a little bit, but the atoms themselves don't change their size, but they vibrate a little bit more. So they need just a little bit more space, right? When they start to vibrate more, they will expand just a little bit, thermal expansion. All right, this thermal expansion, it is utilized when people try to get off like really tough nuts and bolts. Right, sometimes they'll hit it with a blowtorch, right, and they're doing that to try to get that solid to expand so that it'll kind of release the threading in the bolt. All right, and then they'll be able to take it off. I have a really old truck, and I feel like you can't get a single job done on that truck without a blowtorch because everything's rusted together, and it's just what you got to do. You want to take advantage of that thermal expansion. All right, now a liquid, little more spread out. So when we have a hot liquid, it's able to expand a little bit more. All right. And when we heat a liquid, okay, you should be familiar with this. If you ever put something on the stove, if you had a pot of boiling water, when we heat a liquid, now the particles are able to move very easily. So we start to get these currents. If we're heating a pot of water, the heat is at the bottom. So the water at the bottom gets hot, it goes to the top, the cold water comes down. Now the cold water gets hot. So we can kind of get these convection cycles. All right, so it's kind of interesting. That's what's happening anytime you boil water. Now, solids typically are better conductors of heat because they don't allow for that movement, so the heat just spreads through the whole thing very evenly, very quickly. All right, so now the last one is our gases. Our gases, they are moving in random order. And as we increase their temperature, right, that gives them more kinetic energy. They bounce around more, they push more. They'll actually expand the gas. They'll either increase the pressure or they'll increase the volume. In this case, since it's a lid that can move, the volume increases. All right, and we'll see a whole unit on gases. So we'll come back to that. All right. Something interesting about when we have the two different gases at different temperatures, we get this graph. All right. And this graph may be familiar. It kind of looks like the flatten the curve. All right. This is where we want to be. Anyway, the idea is that the average temperature of a gas, all right, is the temperature we see. And when we have a hotter gas, all right, we get a more spread out average. So when we have a really cold gas, a lot of them have roughly the same speed. And again, we can say speed is their temperature. All right, so for a cold gas, we get this distribution where the majority of the gas particles have the same average temperature. As we heat up a gas, we get this wider distribution, but the average is still the temperature. All right, so I just thought that would be interesting since you've seen this exact type of image, I'm sure, at some point over the last couple of weeks. All right, it's called a Maxwell-Boltzmann distribution. And if we had an even hotter gas, it would be even flatter spread out. It would still have its average at the temperature, though. All right, so something that you will sometimes see, and we will definitely see in our gases unit, if we draw a longer arrow, that kind of is going to represent a faster particle. All right, it's covering more distance. The short arrow means it's cold. The long arrow means it's hot. All right, so we're really thinking about heat. We're going to look at a lot of solids actually in this unit. We won't really see the gases too much, but I just want you to think about someone forging a sword. All right, it is incredibly hot. It is glowing. Those particles are vibrating, and the faster they vibrate, right, that means that the hotter the material is. And then as it slows down in its vibrations, it'll actually kind of lose that energy. So this is the formula we're going to use. All right, Q equals mc delta T. You will see this again and again. This is the piece to really leave with this week. Now, Q is the symbol we use for the quantity of heat. All right, so if we're talking about heat, we are talking about Q. Something gaining heat, it is gaining Q. The unit for heat is the joule. All right, it is a symbol, just J. The joule, there can be a kilojoule, that would be 1,000 joules. It's very unfortunate that the joule vape pen became so popular because it kind of ruined the joule. I always love talking about joules, and now I feel inappropriate talking about joules, and it's just a unit of heat, and I should totally be able to talk about joules. So thank you to everyone that just ruined that for me. Really appreciate it. M is the mass. That's nice and simple. We measure it in grams. You will see it sometimes in kilograms. We're gonna keep it in grams in this class, though. Right? In a bigger class, they need a bigger unit, so they'll go kilograms. But we're gonna stick with grams. C is the specific heat capacity, and that it's going to be a quality that every metal, every substance has. I want you to think of specific heat capacity kind of like density, right? When we learned about density at the beginning of the school year, every substance had its own density, and the unit for density was grams per milliliter. Well, specific heat capacity also has units. It's joules per gram degree Celsius. And you'll see that in action in a couple of slides. All right. And every substance has it. And then delta T, that triangle is our Greek symbol delta. It means change. So it's the temperature change. Delta T, it's always T final minus T initial. All right. So the final temperature minus the initial temperature. If we increase the temperature, the final temperature will be greater. Delta T will be positive, right? That means we gained energy, and so now we have a higher temperature. If the final temperature is lower, right? Like when you leave something hot and you let it sit out to cool off, if the final temperature is lower than the initial temperature, you will get a negative value. Delta T can be negative. That just means that something is losing heat. It is cooling off. All right, so don't get upset if you get a negative in any of these questions. All right, so just again for the problem solving, our formula, it's Q equals mc delta T. Q is in the unit of joules. M is in the unit of grams for mass. Specific heat, C, there's that joules over grams times degrees Celsius. And delta T, T final minus T initial in Celsius. We always want to use Celsius. We do not want to use Fahrenheit here. So what happens is when you multiply the gram times the joules per gram times degrees Celsius times the degrees Celsius, the grams cancel out because it's on top and it's on bottom in the specific heat capacity. And the degrees Celsius cancel out because it's on top in delta T, but it's on the bottom in the specific heat capacity. So when grams and degrees Celsius cancel, we get the left side of the equation in joules equals the right side of the equation in joules. So specific heat capacity, it kind of fixes the units for us, right? It gets the grams and degrees Celsius to cancel out. So we're left with joules. So mc delta T truly does equal heat Q in joules. All right. Now the specific heats, all right, liquid water has the highest specific heat, 4.18. And as we go down, solid water, 2.11, water vapor, that's if water is a gas, 2.00, dry air, 1.01, iron 0.45, lead 0.13, copper 0.38. So a lot of our metals have really low specific heat capacities, whereas our liquids, especially water, have very high specific heats. So what does that mean? Because water's heat is so high, it can absorb a lot of energy before it changes its temperature. So that specific heat being 4.18 joules per gram degree Celsius, that means 1 gram of water would need to absorb 4.18 joules of energy to increase its temperature by 1 degree. All right, so there's a really awesome demo. I wish I could be doing it right now. I wish we were in school, where a water balloon, if placed over a candle, right? If it's an empty water balloon, the plastic melts and the candle pops. But if it's if that's just a regular balloon. But if it's a water balloon filled with water, it doesn't pop over the candle. All right, the heat from the candle immediately gets pulled away from the plastic by the water. And since the water can absorb so much energy before it changes in temperature, it doesn't get that hot where the balloon doesn't pop. All right, I used to be very mean to kids in the past. On our 80-minute days, I would set up this demo. I would put the balloon over the candle, and I would tell the kids that they were just going to work on practice problems until the balloon popped. And they're like, okay, it's going to pop soon. It's going to pop soon, because they didn't know any better. And it would be 80 minutes later, and the balloon still hadn't popped. And they'd be like, that's not fair, Mr. L. All right, so it can last a very long time. I did find out, though, that a water balloon over a full blast Bunsen burner, it lasts about 5 seconds before the whole thing pops and you got water everywhere. So that is something that I've learned, but that's a unique property of water. Now, if you were to put a metal over a candle, it'd get hot pretty quickly. You wouldn't want to touch it anymore. All right, but the water balloon will absorb that heat and they'll pull it away. All right, specific heats of metals are going to be important. This will be reference information. You're not memorizing any of this. All right, it'll be either something you solve for in the question, or the question itself will give you this. There are definitely labs that if we were in school, we would be doing, where we would be heating up metals and adding them to water and seeing what happens. All right, we're just not going to have the time for that. But they're kind of a range, but they're all pretty much less than 1. Manganese 1.02, that one's a little bit higher, but typically they're pretty low. All right, but that's a good thing, because that means that metals don't need a lot of energy to change temperature pretty quickly. And they don't need a lot of energy to be cooled down either. So I have a cast iron skillet. Iron has a low specific heat, about 0.45, which is good. That means it heats up really quickly. So when I put it on my stove and I put a flame underneath it, it's hot almost immediately. Whereas if I try to boil a pot of water, it's going to take a couple minutes. I got to wait. I got to putz around and find something else to do with myself while I wait for my water to boil. All right, whereas my cast iron skillet, it heats up real quick, and I can cook whatever I'm cooking in there. And then when I'm done with it, I can just run it under some water, and it'll cool off real quick too. All right, and then I can clean it, and I can put it back. So that's actually a really good thing. It's important for all of our cooking. It's important for our grills. It's important for things like that the metal gets hot real quickly and then also cools down real quickly. All right, it'd be dangerous if it didn't cool down so quickly. All right, so again, our temperature, it's going to be the change in temperature. So you need 2 measurements. You have to record the initial temperature before you add any heat, and then the final temperature. All right, so we have that Greek symbol delta. Delta x equals x final minus x initial. So if temperature goes from 35 to 45 degrees Celsius, then delta T equals 45 minus 35 equals plus 10 degrees Celsius. All right, the temperature increased. If the temperature goes from 45 to 35, well, now 35 is the final temperature. We do 35 minus 45, we get negative 10 degrees Celsius. Temperature decreased, we'll get a negative value. All right, so we just got to be careful in reading these problems to see what the final temperature is, and then subtract the initial from there. All right, so again, Q equals MC delta T. We'll do a little bit of practice with this. The Q, joules, it's an SI unit of energy. The old system was the calorie. All right. So think about it. You've heard the term calories before. All right. We know that when we eat food, it has calories. It's energy. It gives us energy. Now, in the old system, a calorie was defined as the amount of energy to raise 1 gram of water 1 degree Celsius, which sounds a lot like specific heat, which is why 1 calorie equals 4.184 joules, right? Because it's based on water, so the specific heat of water kind of dictated that. And the interesting thing, in like Europe, their food packages will say kcals, right? So, if you were to eat a candy bar and it was 160 calories, out in Europe, it would be 160 kcals, and that K stands for kilo. In America, we did something weird where we made a capital C for the calorie. And so a capital C calorie equals 1,000 calories. All right. So I guess if we're eating 160 capital C calories, we felt better than saying we were eating 160,000 calories. So something unique about our American system of measurements. All right. And again, calorie, amount of energy to raise 1 gram of water, 1 degree Celsius. A lot of the problems we're going to look at will be called calorimetry because it's a way to measure heat. And this is what a calorimeter looks like. This is a lab that I wish we could be doing this week. All right. You can burn a food underneath a can of water, and the heat from the food burning will be transferred to the water. You can measure the temperature of the water, and as a result, you'll be able to see how much heat the water gained from the food. All right, so this is a lab. I remember I did it in high school in my biology class. The biology teachers weren't doing this lab, so I took it. All right, so it's a good one. You get to burn. You can burn a peanut. You can burn a Cheeto. You can burn all different types of foods and see how much energy you get out of it. So if we ever make it back to school, we'll definitely look at this lab. All right, so we're going to do some practice problems, all right, with the calorimetry. This is the important thing. All right, I want you to be flexible with the kinetic molecular theory to have an idea that everything's in motion, and the faster something vibrates or the faster it moves, the more temperature. But I want you to be able to solve Q equals MC delta T problems. All right, so here's the question. How much energy is added to a 300-gram sample of water? Specific heat of water is 4.18 joules per gram degree Celsius. If the water increased in temperature from 25 degrees C to 55 degrees C. All right, so Q is what we're solving for. How much energy? We don't know. Q is our question there. All right, so the mass from the question is 300 grams. All right, the specific heat of water is listed, 4.18 joules per grams degrees Celsius. Now the delta T, it's the final temperature minus the initial temperature, all right? It increased in temperature from 25 degrees to 55. So the final is the 55, the initial is the 25. We take the difference, that's 30 degrees Celsius. So Q equals MC delta T, that means 300 grams times 4.18 joules per gram degree Celsius times 30 degrees Celsius. Grams cancel, degrees Celsius cancel. When I multiply 300 times 4.18 times 30, I get 37,620 joules. All right, so I will have more examples in the next video, but this is the type of information I want you to understand. Solving for Q using the formula Q equals MC delta T. All right, heat is the vibrations, and the vibrations depend on the type of material and how much material. All right.